An isolated solid copper sphere of radius r1 equals 0.12 meters has a positive charge of 6.4 times 10 to the negative 9 coulombs. So, in this diagram, I'm drawing the copper sphere, and we know that it has a radius, which is r1, and that radius is equal to 0.12 meters. So in part A, calculate the electric potential at a point that is 0.1 meters from the center of the sphere. So if the sphere has a radius of 0.12 meters, when we say the distance of 0.1 meters from the center, that's going to be a little bit shy of the surface of the sphere. So the formula for potential, V, is equal to kq over r. The k and the q are known values. The k is the 9 times 10 to the 9th, and the q is the charge of the sphere, in this case 6.4 times 10 to the negative 9. The r is not going to be the 0.10 meters, because this is a conductor, and we know for conductors one of the properties is that the potential is constant throughout the entire conductor, and that potential is equal to whatever the potential on the surface of the conductor is. So we can actually replace this r with an r1. So 9 times 10 to the 9th times the q, 6.4 times 10 to the negative 9, divided by the r1, which is 0.12. And you can notice that the 10 to the 9th and the 10 to the negative 9th will cancel. So when you plug this into your calculator, you will get an answer of 480 volts. Notice that that is the potential for every single point inside this conductor. It doesn't change no matter what. It's the potential at the surface of the conductor, and it's the potential everywhere inside it. Outside the conductor, it's a little bit different, because now it does depend on the distance from that from the conductor. So we're going to use the same equation, kq over r, but this time we can just plug in the value of r for the distance from the center of the conductor. So it'll be 9 times 10 to the 9th times 6.4 times 10 to the negative 9th divided by the 0.24, that distance, and that's equal to 240 volts. I notice that that value gets smaller the further away you get from the conductor, since it inversely depends on the R. For part C, on these axes, sketch a graph of the electric potential versus radius from the center of the sphere and label the value at r equals 0 on the vertical axis. Well, we know that from the center of the sphere to the edge of the sphere, the potential was at a constant, so that should be a horizontal line, of 480 volts. And then outside the sphere, it just becomes an inverse function, so it just drops off in a curve that looks like that. For part D, determine the magnitude of the electric field at a point that is 0.1 meters from the center of the sphere. So once again, we're just shy of the surface of the sphere, so we're looking at the electric field right here. And one of the properties we know of conductors is that at all points throughout the conductor, since the potential is constant, that means the electric field is equal to 0, since the electric field is essentially the change in the potential. So for part D, the electric field is 0, and we can just, if you want to justify that, you say there's no electric field inside a conductor. For part E, determine the magnitude of the electric field 0.24 meters from the center of the sphere. Now we can just use the equation for the electric field because we're outside the conductor. So it's kq over r squared. So 9 times 10 to the 9th times 6.4 times 10 to the negative 9th divided by 0.24 0.24 squared. And when you plug all that into the calculator, you get an answer of 1,000 newtons per coulomb. Or if you want to use the other units for electric field, 1,000 volts per meter. Remember, either unit is acceptable for electric field. And for part F, a second copper sphere of radius R2 that is uncharged is placed near the first sphere, as shown in this figure. So on these axes, sketch a graph of the electric potential versus distance, where the center of the sphere, the center of the first sphere, is at x is equal to 0. So the thing we know is that inside a conductor, the potential is 0. So this first sphere, which we know is a conductor, is going to have a line, a horizontal line. So the electric field is 0, the potential is constant. So we have a horizontal line. Once it reaches the edge of that conductor, it starts falling off inversely. But when it gets to the next one, you've got to have another horizontal line. And it doesn't matter exactly where, since this is just a kind of a more of a qualitative graph than quantitative, but it has to be horizontal, and then outside of that conductor, it's going to continue to drop off as an inverse function.